Before we get started, I have a quick favor. I've been self-funding the Finding Genius podcast for 5 years now. I've done over 3,000 episodes. And as you can see on YouTube, we're up over 1 million views on the channel, which is fantastic. The next thing I really want to push on is to get up to 10,000 subscribers, because once we do, we'll be able to put a donate button, and we'll be able to solicit donations to help keep the podcast running and to also get the Finding Genius Foundation moving along. We have a big project studying anxiety, depression, and PTSD, and working on a product to help people overcome these problems, because I've seen them explode recently after the last 2 years of the whole virus situation. So if you would, please subscribe to the podcast. That would help us tremendously. Give us a thumbs up and check in the description for Buy Me a Coffee. It's about $5. If you could buy me a coffee, I'd really appreciate it. It would help keep the channel going, and I love coffee. Thank you.
Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Hello, this is Richard Jacobs with Finding Genius Podcast. My guest is Dr. Peter Crockford. He's a professor, part of the Faculty of Science in the Department of Earth Sciences at Carleton University. And we're talking about an interesting topic. It came up in an article I saw. How much life has ever existed on Earth and how much ever will? I thought that was a really interesting question. So welcome, Peter. Thanks for coming.
Thanks so much for having me.
Yeah, tell me, about your normal work at the university and what your research is about, and then we'll get into this topic.
Sure. So I just came on the faculty here at Carleton this summer. So to be honest, my day-to-day work right now is sort of building course material and getting grants funded and things like that. But in my previous life as a postdoc, most days was just thinking up new ideas and projects to work on, spending a lot of time in the lab and writing and reviewing papers.
Okay. So how did this question come to your mind? Let's get into it.
Yeah, sure. So during my PhD at McGill University, I was measuring the oxygen isotope composition of like ancient salt deposits. So you can imagine we take some seawater, we sequester it from the ocean, and as long as it's a warm, dry environment, we're eventually going to evaporate a lot of that water. And what's left over is a combination of gypsum, some halite, and some other minerals. And what we found in doing that was that we got these really interesting signatures in rocks that were like over 1 billion years old. And we could relate the signals that we found there to the productivity of the biosphere. And what I mean by productivity is think of the very, very base of the food chain. And we could estimate the rate at which these little microorganisms were producing things like oxygen to the atmosphere. And then over the course of a number of years, we started doing this in ton of different locations, and then we combined this with all sorts of different approaches, and eventually we can cobble together sort of this big question, which is an answer to this big question, which is how much life has ever existed on the planet, which was really fun to do.
Yeah, I've thought about how many people have ever lived over all time, and I saw something on Google estimating about 120 billion by extrapolating back. But so how did you start approaching this question?
So if we can get a rate of productivity at a certain time in Earth's history, we can sort of relate that to how many cells would ever be on the Earth. So today we have 10 to the 30 cells on the planet, which is a huge number that's really difficult to comprehend. It's probably more stars than there are in the universe, for example. And once we have that number in place, we can assume that the rate of primary production, which sort of fuels all the organic matter for all the other things that live on Earth, if we can get an estimate of that at different time points in Earth history, this gives us a way to estimate how many cells would have existed at that time. And if we do that again and again and again over different intervals of Earth's past, we can cobble together an estimate that, in our case, we suggest about 10 to the 39 cells have ever existed on the planet.
But again, how did you estimate that? Did you start with like microbial mats from, let's say 3.8 billion years ago? Like, how did you determine starting conditions, and how did you determine how much life there would have been at a given point?
Great question. So we always like to start in the modern environment where we have much better estimates of exactly what's happening. And by having the modern ratio of productivity to cell numbers, then we could take ancient productivity and relate that to cell numbers. But when we get back really, really far in Earth's past, we have to start making more and more assumptions. So, for example, when did life first evolve on the planet? That's a really contentious question. And the specific date is quite fuzzy. But we believe that it's somewhere between when the Earth finally cooled off enough to have a environment that was conducive to life, something around 4 billion years ago, and when we really see the first evidence of life, which is around 3.8 billion years ago. And so we sort of have a bound, it must have evolved somewhere sort of in those bounds. But because the biosphere would have been so much smaller in Earth's past with, for example, there likely wouldn't have been oxygenic photosynthesis, which fuels most of the planet today. And if the biosphere was a lot simpler and it would have been sequestered to sort of these niche environments, it would be so small that it sort of gets lost in the wash of these calculations. It's only until about 2.4 billion years ago where we have really good evidence that the atmosphere became oxygenated and we would have had a much larger biosphere because of oxygenic photosynthesis just drastically increasing the amount of cells on the planet, that we have the majority of the action happening. And once we have constraints for these sort of critical intervals of time, a lot of the less well-known things sort of fall out in the uncertainty.
Okay, so what is the current estimate? Like, what is production defined as? What is it for today? Let's start with that.
Yeah, so production is the amount of, you can think of it as the amount of CO2 that's incorporated into organic matter. And today that's about 250 billion tons, which is it's about 250 billion tons, and it's produced by, and the consequence of that is like 10 to the 30 new cells produced every year.
Okay. So again, how many are existing at any one point? How many are dying? How many are being created? Is there a net upward trend of life, or is it stable?
So every single year, so if I was to take a snapshot today of how many cells are on the planet, it would be about 10 to the 30. But maybe unintuitively, most of that cell volume is actually in the subsurface or most of the cell numbers in the subsurface. But these are things that are growing incredibly slowly because there's just not that much energy there. But we can project quite deep into the Earth's below the Earth's surface. However, if we just look at cellular turnover times, we actually get a pretty similar number at about 10 to the 30 of new cell production each year. And so when we look at the geologic timescale going from the first life to today, there does seem to be an upward increase in the numbers of cells that have inhabited the planet. When we move into more recent times, of course, that value has probably fluctuated over the past, say 300, 400 million years once land plants colonized the continents. But for the most part, when you look over, say, 4 billion years, it appears that, yeah, we've increased the amount of life on the planet quite substantially.
So what fraction of life on the planet is metabolically active, and which doesn't even really, like you could say it probably almost doesn't participate because it's so slow?
Yeah, it sort of depends on the time frame that you're thinking about. So if I said at this exact moment, okay, likely not as much. Most of the active stuff happening is obviously close to the surface. In terms of the actual fraction, I don't have that exactly off the top of my head.
Well, what's your estimate? What's like a ballpark? Is it a minority of all respiration, and is there a cellular activity? Is it a majority?
Oh, well, if we're thinking about just cellular respiration, certainly like every cell will conduct that to some degree. In terms of, I guess it depends on the units we want to come down on. For the purposes of our work, we're just mainly focused on the primary producers. I'd have to get back to you on how much exactly. Yeah.
No, it's okay. I mean, you were talking about production. So is production, again, linked to respiration, or is production just, again, the cycling of carbon within an organism? Like, again, respiration, I think, would be a major part of that, besides the death of the organism or the birth of it.
No, absolutely. So for our, the main thing that we were focused on was thinking about autotrophs, so the base of the food chain that's really converting inorganic carbon to carbon. But you're exactly right that once that material is produced, things are going to consume it. Some of the material is going to be consumed by the autotrophs themselves. And so there's going to be a cascade of things. So for our work, we just related that first step of primary production to the total amount of cells and new cell production on the planet.
Well, what about organisms that subsist off of sulfur or methane?
Yeah.
Are they significant fractions of the total biomass? Did that skew the numbers?
So not as much, actually. So certainly for the Archean, say pre-2.5 billion years, these would be much more significant contributors to the overall biosphere than they are today. But in terms of overall, we put those in the basket of, say, chemolithotrophs. These are things that are making a living off of rocks and sediments and other forms of energy on the planet, they would have dominated for a while, but today they're in the minority, and oxygenic photosynthesis just really dominates the Earth today.
So they are a majority? I mean, you know, in places where, again, sulfur bacteria are utilizing the surrounding sulfur, because they're bacteria, I would think they would have tremendous numbers, but even so, they're a tiny fraction of all the existing organisms?
Well, a tiny fraction of all the production. So certainly down in the deep subsurface, you could have really slow-growing things that are making a living in a number of different ways. The exact proportion of what metabolisms are operating as we get into the deep crust, I think that's something that's ongoing. There's a lot of people focused on the deep biosphere, but of course, it's not an easy part of the Earth to study. But in terms of the majority of, say, biomass produced year to year, that's going to be oxygenic photosynthesis dominates that.
Before we continue, I've been personally funding the Finding Genius podcast for 4.5 years now, which has led to 2,700 plus interviews of clinicians, researchers, scientists, CEOs, and other amazing people who are working to advance science and improve our lives and our world. Even though this podcast gets 100,000 plus downloads a month, we need your help to reach hundreds of thousands more worldwide. Please visit findinggeniuspodcast.com and click on Support Us. We have 3 levels of membership from $10 to $49 a month, including perks such as the ability to see ahead in our interview calendar and ask questions of upcoming guests, transcripts of podcasts you're interested in, the ability to request specific topics or guests, and more. Visit findinggeniuspodcast.com and click Support Us today. Now back to the show.
So the trend has been, now it appears to be at a stable level, or is it trending up or down?
If we were to look over the past, say, million years, and we take our cues from the ice core record. So the longest continuous record of ice, I think that they pulled up in Antarctica is about 700,000 years. Sorry. The oldest ice people have found at this point, I think is about 2 million years, but this isn't really a continuous record. But within that ice, there's little bubbles that contain CO2, O2, and give you a nice sample of the atmosphere. And when people have looked at the isotopes of that O2, they've come up with estimates of the productivity of the biosphere in a similar way that some of my PhD work did using ancient salts. And it appears that global productivity hasn't varied too much, which is a little bit unintuitive when you think of the last glaciations, for example. And the idea is that maybe the marine realm became a bit more active over these intervals of time. When we go further back, there might have been higher productivity, say, for example, in the Mesozoic, around the time when dinosaurs were around. But when we look on very long time scales, it appears that we're sort of in this stable, high productivity interval at the moment. Yeah.
What percentage of all carbon on Earth is cycled by life? Is there an estimate of that?
If we were to look at the total amount of carbon on the planet and ask how many times has the biosphere cycled that, for example, we would get an estimate that's about 100 to 1,000 times the amount of the total amount of carbon on the planet. So what does that look like? If you were to look out at the moon tonight, now just imagine all of that is just a ball of carbon, okay? That's about the amount that the biosphere has cycled over the entire lifetime of the planet, which is pretty impressive.
Yeah, but in relation to all the carbon on Earth, you say it's about 1,000 times, but over a huge time scale.
Yes.
So let's relate it to a year, what is the total production effect? What percentage of the carbon does it cycle?
In terms of a percentage...
Yeah, even if it's real crude, what would be your estimate?
Let's see here. I think it's 110 million a year.
Okay, so it's a very, very small fraction of all available carbon.
Keep in mind, though, that most of Earth's carbon is not at the surface. Okay, most is tied up in the deeper Earth. So the biosphere does not have access to... So in terms of the amount of carbon that's actually at the surface that the biosphere even has access to, certainly that number goes up quite a bit. However, I don't have...
Can you call that available carbon? And is there an estimate of how much there is there?
Well, you could think of it as say the amount of CO2 in the atmosphere just as a reference point, and that would be about a quarter of it every single year.
And what about the fraction in soils that plants and other creatures would have access to, and in the sea?
That I would have to get back to you on because I don't have those numbers at my fingertips right now, or the amount of dissolved organic carbon in the ocean in terms of real numbers at my fingertips here.
Okay, well, understanding these numbers, what does that lead to in terms of thoughts? What consequences are there? What you figured out?
I think we're living in a time right now where we're looking at exoplanets. We're actually starting to contextualize Earth in relation to a lot of these other new planets that we're discovering every day. Of course, we don't have direct imaging of these things. A lot of our observations are simply sort of the amount of time it takes for these to orbit around their home star, maybe the mass of these things. But it's certainly caught the attention of a lot of public's interest, and a lot of researchers are thinking very hard about what these planets could be like. And one of the fun things about this work is that it sort of provides a benchmark of just, at some point life originated on this, third rock from the sun, and how much has it been able to house over that, say, 4 billion years of biospheric history to now. And we can even go further and say how much life will ever exist as the sun continues to heat up, and eventually at some point the Earth will become uninhabitable. But this provides a benchmark to compare some of these other planets to, especially when we think about water worlds or places that we think could be habitable, which I think is a fun thing to think about. On the other side, when we think of just exploring our own solar system, one thing that this work really made me think deeply about was, like, for example, when I was a kid and I would read Arthur C. Clarke's work on, 2001, 2010, 2061. And there's parts of that book where they go to Europa and there's these creatures there and things, where I think doing this work really made me think deeply about how much evolutionary time you have and how many cells you really need for that, and that the odds of finding anything that's not just like a very, very simple organism is effectively zero in some of these icy moons, for example.
So what do you think will be the trajectory of life, over the next, 1,000 or so years? Will it be stable, or is it going to experience some significant difference?
Over the next 1,000 years, I think that's really our choice as a species. We're sort of endeavoring on early steps of sort of planetary engineering at the moment. There's discussions about injecting aerosols into the atmosphere to manage the albedo of the planet, to sort of govern the temperature. There's work to be done to pull CO2 out of the atmosphere, but even if you think of just how much we're putting in, these are very large-scale planetary experiments that we're running. And so I think over the next 1,000 years, it's really difficult to predict because humans are becoming such a powerful influence over that. So that, I think, is challenging to say. I would say that if we continue on where we are today, and saves that no major wars and certainly not nuclear wars, then hopefully it's at a similar level that we are today. Moving forward, though, at some point that's going to change quite drastically.
Going back in time, though, I just realized, were there periods where the production was way down, let's say during the last, active ice age, or during a period where there was tremendous volcanic activity? Can anyone see that, the historical record of climate?
So in terms of the last ice age here, the ice core work that I was alluding to sort of showed that the amount of productivity on the planet on the whole doesn't go down a heck of a lot, which I think is a really surprising finding. Even if you look at, say, major extinction events, so say the Cretaceous-Paleogene boundary, yes, there was a major reduction in the productivity of the planet, but it only lasted for a relatively short interval. And so, yes, there would be a period where things go down by a fair bit, but microbes can bounce back quite fast. In terms of long durations where the amount of life on the planet and productivity dropped extremely substantially would be during an interval of time about 720 million years ago to 635 million years ago, which is this interval called the Cryogenian. And over this time, there was 2 what are called snowball Earth glaciations. So the whole planet would have been covered in ice from pole to equator. And over one of these states, you would have had a major barrier to photosynthesis in marine waters with all of that ice. Life likely would have been confined to little cracks in the ice, maybe little ponds on the surface, and the amount of production on the planet would have gone down enormously. And that would have been sustained for the durations of these glaciations, which the best estimates today, I believe, suggest the first one, the Sturdian, lasted 55 million years, and the second one about 5 to 10 million years. So these would have been major productivity drops in the biosphere.
Well, were they? Was this corroborated with ice cores, or did it not seem to corroborate?
No, sorry. These were events that are 720 million years ago.
Oh, okay.
So, yeah, these are just our inferences that we can make from the geologic record.
Well, what do people think was happening during the last ice age so that productivity barely fell?
Well, I think it really comes down to nutrient cycling in the ocean and ocean circulation. So this is something that's still actively being worked on. So the dynamics of, say, carbon moving from the ocean to the atmosphere during these glaciations is still a big problem that people are still trying to figure out. And so the simple answer is, of course, productivity just went up in the ocean, and it was probably because there was more nutrients in more regions of the ocean than there are today, and that sort of kept productivity at a relatively similar level to today, even though the northern hemisphere was much more covered in ice. But exactly how that worked, there's a lot of people working on this, looking at marine records and trying to figure out exactly how these environments function under quite different conditions.
Okay. So what are some questions you think that all this work will generate, now and in the future for other scientists?
So I think that one thing that came out of this was that there's some intervals that we just clearly need to understand a little bit better. So of course, in our work, we present some uncertainties that we just can't get past at this point. And a lot of that centered around a time period, which we collectively call it the Great Oxidation Event. So that would have started around 2.4 billion years ago. And this is when Earth got its first significant O2 into the atmosphere. And there's a lot of debate exactly what the dynamics at this time, the ultimate trigger, was it the evolution of oxygenic photosynthesis, or was it just this metabolism kind of got supercharged and emerged to be much more ecologically prominent? That's still debated quite a bit. But over this interval of time, productivity estimates vary by a huge amount, so by orders of magnitude. And one of the kind of crazy things that happens when you're living on a microbial planet is there's nothing to really buffer you against extremely high O2. Not in the same way, at least as today, where we would, if we put O2 too high in the atmosphere, we're going to end up with a whole bunch of forest fires that's going to bring us back down. And what our study showed was just really sort of highlighted this uncertainty and how you can imagine two completely different trajectories with, maybe 1,000-fold difference in the size of the biosphere over this, 100 to a few hundred million year interval. And I think it really draws attention to that specific time and really calls a lot more work to be done on it to figure this out in much more detail.
So what does current analysis of production do for it today? What does it tell us?
You mean in terms of just understanding primary productivity in the modern environment, or?
Yeah, like in the modern environment. I mean, it's been stable for quite a long time. It's like, is barring any crazy events or mega shifts, it should stay at kind of about the same level, is what it sounds like. But is there any other benefit to understanding it?
Certainly the major players is important to think about. So today this is being done by a combination of trees, marine algae, cyanobacteria, understanding the distribution of those things, what species have sort of taken over at different times to become more and more important, is just an interesting question, seeing as, it's one of the major parts that drives sort of Earth's biogeochemical cycles. I think that's very interesting for academic reasons. And then you sort of go down and think about, in a more granular scale, of just, forest health. What happens if we make major changes over landscapes and things? Those sort of lead to more interesting questions. But some of these big numbers, just looking at a planetary scale, when we don't really expect it to change much, I'm not struggling to think of exactly what people do with those numbers on a day-to-day basis. Probably not a lot, to be honest.
Well, if people try to segment, production to different, to again, the water, to the air, to different biomes, maybe then you could evaluate, all right, production should be this in the desert, but it seems to have gone way up or gone way down for some reason.
Oh, absolutely. Yeah. Yeah. And within specific regions of the planet, it gets quite interesting. That's exactly right.
Any those are conclusions from looking at it in specific regions? Has anyone done this?
Yeah. So there's actually tons of work being done on this. Of course, you can imagine, like, what are the consequences of sort of transitioning huge swaths of the Amazon from jungle to agricultural land, or understanding, for example, exactly where productive zones are in the ocean and where unproductive zones of the ocean is also very interesting. An example of that would be, one climate mitigation technology that's on the table is basically dumping things like iron into the ocean to fertilize it and use that as a climate mitigation strategy. So that starts with sort of having an idea of how different regions of the ocean operate and having a very deep knowledge of exactly what that ecosystem is lacking and what would happen if you were to add that missing ingredient and how much bang for your buck would you get. So those sorts of things, I think, is where some of this sort of bubbles up and becomes much more relevant to many pressing questions today.
Well, going forward, how does this dovetail with your intended research?
So my work is mostly focused on just trying to refine our understanding of Earth's past. And looking at the productivity of the biosphere, how much life has been around is one aspect of that. But there's other things that we also want to think about. How much oxygen was in the atmosphere through time? What were CO2 levels? How reliable is the rock record that we're looking at? And how can we sort of make checks and rechecks? And the way you have to do that is go out into the fields, gather samples of the right age, take them back to the lab. I would say do the analyses, but I'm sort of at the stage now where it's train students to do the analyses and then share it with the community. So that's what I have to look forward to for the next while.
Yeah, very good. Peter, what's the best way for people to, to follow your research and to see more about what we've spoken about today?
Yeah, so check out my website. It's just petercrockford.rocks. Check out web pages at Carleton University, or look up on Google Scholar, or find me at EarthJapede on Twitter. And yeah, that's usually where I'll post latest and greatest stuff coming out of the lab.
Okay, very good. Well, thank you so much for coming on the podcast. I appreciate it.
Yeah, thanks so much for having me.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.